So today we're going to start talking about Newton's laws of motion. It's going to be a series of videos. So today is the first introductory video. So I'm going to choose the simplest possible system that I can think of, a box sitting peacefully on the floor. Let's say the mass of the box is m, and later on we will give it a value like 2 kilograms or 3 kilograms or whatever. So the first force that we can think of is the force of gravity. That's the weight of the object. So what is the weight of an object? It's the force of gravity with which the planet, in this case our Earth, pulls the object towards itself. Since the force of gravity acts on all particles of the box, I'm going to draw the force of gravity from the center of the box. Now notice that when you draw a force vector, you must attach the vector to the object experiencing the force. Now in this case, this force is exerted by the Earth. I don't put this arrow attached to the Earth, but I draw it attached to the object on which the force is acting. Okay, so what's the magnitude of this force? So coming back to this box, the Earth is pulling it down with a force mg, which in this case is 20 newtons. So why doesn't the box go right through the floor and accelerate towards the center of the Earth? That is because the floor does not allow it to do so. To understand this, you must think in terms of atoms. The floor is made up of atoms which are held together in a lattice tightly. And when the atoms of the box try to go through the atoms of the floor repel them. And that's a repulsive force because of the following reason. If this is the floor and this is the box pushes down on the floor, and the floor, by Newton's third law, pushes back up on the box. Since the two forces, action and reaction, act away from the two objects, it's a repulsive force. So what's the nature of this force? This is a force between one set of atoms and another set of atoms. It's an interatomic force. So I'm going to draw this force on the lower surface of the box because that is where it acts. It's a force between the two surfaces which are pressing against each other, and this force, let's give it a name, we'll call it R. So R is the force exerted by the floor, that is the top surface of the floor. The atoms on the top surface of the floor, on the atoms of the bottom surface of the box, and they keep the box from going through the floor. This force, unfortunately, has been given the name normal reaction. 200 years ago or something, somebody gave it the name normal reaction. Unfortunately, they did not consult me. I would have told them just call it force of contact. But no, they decided to call it normal reaction, thereby causing confusion to generations of students who think that this is the reaction to gravity. That is not true. Let me illustrate that. Here is the Earth, and let me separate the box from the floor so that I can draw the forces clearly. So first we have the force of gravity on the box. Who is exerting that? The Earth. What's the reaction to that? Box pulls the Earth back with an equal and opposite force. So if this is 20 newtons, the force on the Earth is also 20 newtons. So this is an attractive gravitational action-reaction pair. Box pulls the Earth, Earth pulls the box. Either one can be called action, the other one is reaction. It doesn't matter which one you call action, which one you call reaction. They act simultaneously between the two objects. So the normal reaction is not the reaction to the weight. The reaction to the weight acts on the Earth, and it's an attractive force. So action and reaction act on different objects. In this case, one of them on the box, one of them on the Earth. And now let's draw the normal reaction force. The normal reaction force is a force exerted by the floor on the lower surface of the box. So this is the normal reaction. Who is exerting that? The floor. What's the reaction to that? The reaction to that is the box is pushing down on the floor. So if I call this R, that acts on the box, and this is also R, which acts on the floor. Again, action reaction act on different objects. As you can see, we have two action reaction pairs. One is the attractive gravitational action reaction pair, and one is the repulsive force, interatomic in nature, between the floor and the bottom of the box. So this R, which is acting on the box, and this 20 newtons acting on the box, one comes from one action reaction pair, the other one comes from a different action reaction pair. So R is not the reaction to the 20 newtons. So R need not be equal to 20. Need not be. And I'm going to give you examples where R is not equal to mg. But for this particular problem that we are solving, take a look. We have R and mg. And if I take upward direction as positive, we have plus R minus mg is the net force, should be equal to mass times acceleration of the box. But we see that the box is not accelerating. It is sitting peacefully on the floor. So the acceleration is 0. So in this example, R turns out to be equal to mg is equal to 20 newtons. So in this example, where the box has 0 acceleration, the normal reaction turns out to be equal to mg. Remember, it's not the reaction to mg. So this is 20. This is also 20 newtons. So I'm going to stop this video here, and in the next video, I'm going to give you examples of situations where the normal reaction is not equal to the weight. So wait for the next video. Until then, goodbye.